So I'm Tom Beattie. I'm Research Director at Prelert. I don't think I didn't quite budget for the time I've got, so I might slightly have to rush through a few sections, but hopefully it'll be okay. So, talk outline, why do you want to do anomaly detection, talk about use case of our product, then there's a massive amount of literature on anomaly detection, thousands of publications a year actually at the moment, so some background on that. Then I'm going to talk a little bit about machine data characteristics, so those are the data sets that we work with. Then how do you design analytics to work at really large scale, because there's some constraints you have to deal with. And then a couple of case studies of the analytics we do. I'll try and, I couldn't sort of talk about everything, but I just focused on a few aspects. So, just quickly about us, we're trying to do this package solution to do anomaly detection in time series data. We built our product on top of a database called Splunk. Initially, we have an open API now that takes stream data. We designed our approach from the outset to scale to very large data sets. And we also designed it to operate in a data stream setting. So that means basically you're getting data sent to you all the time. It might or might not be stored as well, but we don't assume it has to be stored. And its characteristics typically change over time. And also, finally, our software is aimed at statistical lay people, so we can't present them with things that are difficult to understand. We have to we have to usually display pictures that they get and they can interpret. So why do you do anomaly detection? Well, many practical tasks, and we saw one in the last presentation, boil down to anomaly detection. I just tried to list a few here. So the thing that we started out looking at was detecting faults in IT systems. So that's typically changes in or unusual values in the operation of an IT system, and you're monitoring in all sorts of different ways. I went to quite a good talk actually recently on looking at unusual patterns in satellite imagery, particularly to look for deforestation and fires. You get a change in the kind of green profile. Then detecting problems in planes, mechanical devices, congestion, traffic networks. That's actually a use case that I'm going to talk a bit about. Malware detection, network intrusion. Those are slightly different. You're looking there at a population of users, and you're trying essentially to find users who are doing things that are unlike other users. Road traders would be another example of that. And basically, it's a fundamental tool of data mining, and it adds value to many data sets if you can reduce them to a few key things to look at. So, very briefly on the use case, this was just a proof of concept. So, Transport for London wanted to monitor congestion on bus network, and they also had a database of faults that they knew about on their system, and they had a location and a time for those, and they wanted to correlate those with congestion so that they could potentially rank them and prioritize fixing things. The bus journeys were actually broken down into links, so you had time series for each link. So this would be a particular section of this doesn't show very well. Anyway, this is a particular section of a route, and in total there are about 2,000 routes, and they obviously display kind of daily and weekly patterns, and you get value outliers and potentially not perhaps so much pattern outliers in this case, but outliers in context certainly. And we would produce output like this essentially, so we would detect a period of unusually long journeys, and we get a list of the links that are affected at that time, and also we associate probability with those. I'll talk a little bit about that later on. And produce views like this, so you'd have kind of lateness, anomaly view, and general health of the system on a map. and then they would also have, as I say, these faults, and we would correlate those and rank them by the amount of delay, total delay they were causing to journeys. Okay, so that was a use case. So general anomaly detection, and we talked a bit about, there was a bit about this in the previous talk. So generally people kind of try and identify broad categories of anomalies that you might care about. So a point outlier, that's probably the kind of classical definition of an outlier or an anomaly. You have a cloud of points and another point that's somewhere away from that cloud outside the, but it could, this could be an unusual shape. I mean, I made it very simple there. An outlier in context, so that's where the value in itself is not atypical, but because it's happening at a particular time, in this case at the sort of a period where this time series is unusually high, or at its peak, that value is unusual. Bulk and pattern anomalies. So we saw examples where you could apply that pattern anomaly to a time series because it has shape, but you could also apply it to sequences of characters. The key thing here actually is that you often want to find how to construct these patterns as well as identify what's anomalous at the same time. So the problem here was actually splitting the data up in this way such that something emerged, and that actually is quite a hard problem. So as opposed to having to find the patterns, having to find what to look for, if you just have a fixed dictionary that you work on, then rare values are certainly anomalous. And then finally, a kind of structural, I'm calling it structural because you get quite a few papers about anomaly detection on graphs, and actually time series display a similar property. Here there's the feature of this, the shape of this, or actually the generative process of this time series changes at that time. But you couldn't really boil it down into a particular pattern change, something in the generative process of that, something in the structure of that data changed at that point. So basically what you measure is very important, and most anomaly detection happens in an unsupervised environment. You don't have someone who's marking up what they want to know about. They want you to tell them what's unusual in their data set. In this case, the figure on the left, you obviously can't, in an unsupervised fashion, differentiate those crosses from those circles, but if you happen to measure the right feature, they become very simply separable by some plane, at z greater than 0. And in the same way, on this time series, it was visually perhaps clear that something was going on, but in this case, because I know what the generative process of that time series was, I know that that essentially the variance in a small time interval changed at that point, the smoothing of the Brownian motion, that if I calculate the variance in a window, then I can detect that change very simply. So as I say, a lot of papers on this. This is a highly cited paper. This was a distance-based approach by Knox and the idea is that you have a distance that for which a fraction of the data is further than that distance from you, and you find the largest distance such that a fraction of the data is further than you, and you can imagine different, well, it would depend on the distance metric, but you'd have contours here for which, for a different value of f, the distance would change, and outliers would be points that are more than, that have unusually large values for this distance. So that was criticised, and the criticism was that it didn't happen, it didn't handle cluster density very well. So the point on the right isn't an outlier because in the context of its cluster, it's fairly typical. The point on the left is atypical for its cluster because the distance to it, from it to its neighbours and its neighbours to their neighbours, is unusually large. Or the ratio of those distances. So if you have a predictive model, then you can do things like manoeuvre detection. So here we're predicting where the value is going to be, and an outlier would be something that lands away from where we're predicting. You know, Kalman filtering you can use to do that sort of predictive process if you believe that there, or if you have some grounds for assuming a particular dynamical model for whatever you're looking at. And then, yeah, an outlier is something that just lands up away from where typically you have some uncertainty in the prediction, but it lands up in the tail, you know, the tails of that prediction. So principal component analysis actually is quite an interesting approach that uses robust principal components analysis. The idea is that you decompose a matrix, that you turn your data into a matrix, you decompose it into a low rank component, so that would be a subspace, a dense component, so that's rank full, but it's small in magnitude, and then you have a sparse component that has large values with respect to E. So those are values that lie a long way from the plane with respect to the size of the eigenvalues of your rank full matrix. Actually, I think they're not presented in these terms, but I think these all boil down to the same thing. Essentially, you're trying to estimate a density function and then looking for points in the tails of that distribution. So the first distance measure, well, that's exactly what you're doing when you have uniform density in your cluster. You know, it's actually very like a kernel density estimator. Local outlier is actually even more like a kernel density estimator. So it's essentially accounting for the impact of cluster density on the distribution. Predictive model, where you have a path-dependent density function, and principal components, you're doing this where your density is a subspace, and you're doing it robustly as well. And just to make that clear, so perhaps talking about distance to your neighbour and distance to their neighbours is not so clear, but if you look at contours of the sort of distribution you might fit to that data, then very clearly the point on the right isn't really in the tails of the distribution, the point on the left is in the tails of the distribution. And okay, so you have a probabilistic model, or you have a density function, whatever. How do you compute anomalousness? I won't go into that really now, but there's a link to a paper online which essentially defines a way that you can compute a probability that relates very closely to what I think most people would agree is a good definition of anomalous. It's the event of seeing things that are less likely, have lower density, and it works when you've got clustered data and various other things. So is this the answer? You just get a really good density estimator and you compute some score related to how far into the tails the point is, and you're done. Well, I'm just going to very briefly talk about two big problems, and I suppose they affect all sorts of things. So survival theory, if you live to a time t with probability t, and then you have an independent chance of dying in the next interval delta t, then your probability of surviving to t plus delta t is just the product of those two probabilities, and you can turn that into a differential equation. You get an exponential distribution. Well, if you have uniform points in an interval, then in fact the distance to your nearest neighbour is at least r, is governed by exactly the same equation. So in 2 dimensions, I'm assuming everything's Euclidean, you have this extra term, this extra r term, because the volume of the shell essentially is proportional to the radius. So as you increase the number of dimensions, the volume of the shell grows with respect to the volume of the ball, and the thing is that points then become increasingly uniform. And so this is the case where you have just uniform data in dimensions 1 to 10, and you say, well, what's the distance, what's the distribution of the distance to my neighbours? And in fact, you can see in 1 dimension there's quite a large dispersion on that. In 10 dimensions, there's a very small dispersion. And as you increase the number of dimensions, this goes to something like a step function. So trying to discriminate points based on a distance when there's no variation in the distance is not a very good idea if you have very high dimensional space. Okay, so that's one problem, and dimension reduction techniques do help there. Probably the right way to go, in fact. But there's another problem, which is, you're assuming essentially that you have enough data to be able to estimate this distribution. And if you have 10 points to estimate a distribution in one dimension, in 10 dimensions you need 1 billion points to get this, 10 billion points to get the same resolution. So if you see something odd, you don't necessarily know whether it's just that you haven't got enough data, that you haven't seen something in the vicinity, or whether it's genuinely unusual. So very detailed structural anomalies, very detailed structure in your probability distribution can't really be resolved in high numbers of dimensions. So you have to essentially simplify your models. You don't always want to use the most, the most non-parametric approach. So just to, it affects the number of parameters you use. In this case, I was just looking at Gaussian distributed points, and I was fixing basically the probability. So you can generalize the notion of cumulative density function for a Gaussian into to handle multiple dimensions. It's just like the probability that it's outside. It's the probability that it falls outside a contour radius. The man-Lopez distance, in fact, and it is it's a gamma function. So you have to adjust basically the distance of the point to the mean of the distribution as you go up in dimensions. But if you do that, then you can ensure that you have essentially the same probability for each dimension. We should have the same probability for this point in each dimension. And what I have here is just an illustration of this as you go from 1 dimension to 15 dimensions. So here, in 1 dimension, I've estimated the mean parameter and the variance, 2 parameters, and that point would live sort of. So these are the probabilities. This is the log minus the log of the probability, and this is over 500 different trials, different random samples of the of the Gaussian. This is the log of the probability of that red cross in 1 dimension. This is the log of the probability in 5 dimensions, 10 and 15. And you can see by the time you're estimating the full covariance matrix, so that's n plus 1 over 2 parameters plus the n parameters for the mean, the uncertainty in your probability estimate is really large. You can try and account for this, and there are 2 ways to do that. You can look at a kind of Bayesian approach where you estimate the distribution of the parameters of the model you fit, or you can bootstrap like this and look at how much variation you're getting. Is this thing really significant if I randomly resample the distribution? So in high dimensions, data is very uniform, sparse, and generally you want to avoid doing full multivariate analysis. You want to look at essentially when the data lies near some low-dimensional manifold, or if there's some factorization, if there's some independence in your distribution function, then you have to have a way of aggregating across anomaly scores for different marginals. Again, there are good ways of doing that, and there's a paper that links on our website for ways of doing that. There's a link from our website on ways that you can aggregate. So insight isn't always actionability. Basically, if you tell someone that their system is operating in the tails of a low-dimensional manifold, they generally will look blankly at you. And that's a function of user expertise. So you have to present pictures to people that they get, and doing that in multiple dimensions is quite hard. The other thing I would say is correlation is always useful. So if you can detect that anomalies in 2 time series happen at the same time, and generally happen at the same time, more than you'd expect if it was just random, then that's really interesting because it could imply a causal relationship. So in machine data, you basically have a load of data characteristics you need to handle. It's periodic, you get these sporadic features like bank holidays, you get domain-restricted quantities like percentages, you have lots of different data types, integers, real values, categorical data, there are correlations because of load balancing. Very little is Gaussian, in fact. If you look at the distributions of residuals of fits to time series and things like that, characteristics are changing, you're getting as a data weight, and you're getting this stream of data that varies in the number of events you're getting per second. So you can't necessarily slow down a great deal when the data rate goes up. 1 million plus metrics for a big system isn't unusual. And I tell you, if you have any sort of false alarm rate and you're looking at 1 million metrics, that's a lot of alarms. So thousands of events a second and terabytes an hour is not uncommon. And net flow data is massive. People aren't really storing it because it's too big. That's the traffic on a network. So how do you go about trying to do anomaly detection on this? Well, one thing is that you want to first of all aggregate your data. You can't get your data to a single process. Typically, it's stored in a distributed fashion. You can't transport it all to one place. So you want to map it into features that you can then significantly reduce the volume of data. So they're simple statistics like count, minimum, maximum, mean, value, and those are obviously you only need to in order to aggregate a count, you just have to sum it, and you just need to pass the count. So you could have turned 1,000 events into one number. Actually, there's an interesting problem of looking for features like this offline that you can then map produce, and things like autoregressive models you can do that on, and least squares fits, things like that. Anyway, the key thing is that because you've mapped your data to a small set of feature, a much reduced data volume, you can then scale to pretty much arbitrary large systems. And you also, this process, provided it's cheap to compute this process essentially doesn't work. You don't slow down a great deal as the data rate changes. I mean, your throughput doesn't slow down, your data throughput. So you might think that this was a disadvantage, but it's kind of poor man's pattern anomaly detection. So in this process, if we looked at these values, it's not perhaps particularly clear that there's anything unusual. You might say around 500 something happened. That's the distribution of those values, just so they're over histogram over time. If you now look at the time, the mean in a time window, then you can see very clearly, because the variance is the noise was uncorrelated, that essentially there was a step change in the mean of the process at that particular time, and that corresponds to going from the left-hand feature, the left-hand cluster to the right-hand cluster, and that would be easy to detect. With any sort of online approach, you basically get to see each piece of data once. It's suitable for streaming environments, and particularly where data characteristics are evolving, and it allows you to scale to pretty much arbitrary large data sets as long as you can keep up with the data rate. So actually, there are very good viable optimization techniques, so you can use fairly sophisticated machine learning approaches with things like stochastic gradient descent. But things like clustering in an online setting is really hard because you're forced to make irreversible decisions, or you might be forced to make irreversible decisions. But basically, if you want to handle a huge data, anomaly detection of huge data sets, and particularly in the environments where people want to do that, which is where they do it as data's arriving, essentially get an answer back as quickly as possible, then it's worth it. So just to very briefly look at a couple of things about detecting, about sort of predictive modeling, if you like. So for periodic trend, first thing, once you've found a periodicity, there's no real chance of overfitting the data because you typically have lots of periods to look at. So you can use non-parametric approaches. So this is, I think, quite an interesting result. Is if you just want to minimise the over all functions, all periodic functions, minimise the square of the residual. So x is just an arbitrary function. This is a functional minimisation. F is our target function. You've got some additive noise. Then just taking the mean value of the function over a given time over all periods is the right function that minimises this first equation, or that solves this first equation. So a really simple strategy is just to bucket the data, bucket the period, compute means. You just need to store a count and a mean value in order to update that, and you can update it online. And yeah, you have to interpolate then that in some way, and splines actually work very well. When you have data which has spikes or a sharp step change, any interpolation technique like radial basis functions that is supported over the whole interval tends to be unstable and tends to have these kind of weird sort of load-like effects around these sharp points. A really important thing to think about when you're trying to design anything, I think, particularly when you're trying to deal with large amounts of data, like lots of time series, that sort of thing, is your kind of essentially your memory to QOR. So a good example would be, don't just use a fixed bucket pattern. You adapt the bucket pattern to essentially minimize some quantity that would be related to how quickly the function's changing. And that sort of consideration comes up, it comes up again and again. Clustering data, as I said, is hard. So it's because you have to make these irreversible decisions, and those can have bad consequences. So essentially, you try and avoid making irreversible decisions if at all possible. And the better state of the art for doing that are things like essentially sketch data structures. So you don't actually try and cluster the data as it goes. You keep back you fix the amount of number of data points you want to store, and then you cluster the sketch of that data. And then if you blow your memory budget, you have to merge points. So it's like a kind of overly granular clustering that you then run clustering on top of. And if you're doing clustering with, say, a mixture of Gaussians, think about whether you want to use spherically symmetric or full covariance matrices, because this first one, you need one parameter, one double cell, 16, 8 bytes rather. This second case, you need n plus 1 over 2 times 8 bytes, and it might be better to actually use more spherically symmetric Gaussians than a smaller number of arbitrary Gaussians. And this just illustrates why it's hard. If you've seen to that point those data points, it's difficult to say whether those two blue points are unusual or not. Obviously, if you then waited a while, it would potentially become clear that those were outliers. You shouldn't have clustered those with your other data. Finally, just briefly talk about tail behavior. So essentially, anomaly detection happens in this region. So this is, we talked about fitting distributions to data, and and that Gaussian visually, okay, it's not a great fit, but it doesn't look too bad, it fits the bulk of the data. But the key problem is that in this region, where you have little data, the fit of that distribution to the data is generally very bad, or it can be very bad. I mean, it's this kind of fat tail distributions, essentially. A key thing to think about is expressiveness in tails, so being able to fit different types of tails to the data if you want to do outlier detection. So, you know, be able to fit something which is essentially a power law tail. You know, that massively improves your false alarm, recall false alarm. Okay, thanks.
So we have a few questions for Tom. We're a bit short of time. We really want to have the full length of Sean's talk, right? Any questions for Tom? You're going to be around, or you?
Yeah.
Yeah. Okay. So people can ask you things later. Then.
Okay.
Yeah. So we can do a very quick, short break. We need to come back and